Like we talked about the constant, well, no, we talked about the additive property of integrals yesterday, just kind of quickly mentioned it. If you have a definite integral with two functions added or subtracted, you can separate it into two integrals and find this integral and then add them together. If there's a constant inside, just like derivatives, you can pull that constant out in front, right? And have the k in front, and then find the definite integral and multiply by k. This additive interval is pretty cool. We did it the other day with the little triangle problem. If you have two areas that are separated, like you have A to B, and then C is in the middle, you can do the integral from A to C, and then from C to B, and add those together, right? Instead of going all the way from A to B, you can go from A to C and then C to B. But what's actually pretty cool about this is that C doesn't have to be between A and B. You can pick a number over here and do that, and this property would still hold because some of the areas can end up going backwards and canceling out the area of the other integral. So you can pick any number you want and split this up into two integrals. That'll hurt your brain a little bit if you think about it too much. We talked about this one down here. The integral from A to A is going to be 0, right? How's there any area if we're going from 3 to 3? Well, there isn't any, right? And then this one we kind of talked about. This is kind of like the backwards thing. If you're going from B to A and you switch the limits, you make it negative, right? So that's why when it's going backwards, it becomes negative. So if you want to switch the limits, you make it negative. So let's use these properties to evaluate some definite integrals. Here, we have the integral. We want to find the integral from 1 to 3 of f of x plus 6, and we know the integral from 1 to 3 of f of x is 10. The most tempting answer for this, and I'm sure a third of you will do this at some point, is to say, oh, it's 16. Because the integral from 1 to 3 of f is 10, and we're adding 6 to it, right? But remember, you're adding 6, and then the area underneath 6, right? You're not just adding 6, right? You're integrating 6. So we have to split this up into two integrals. We can't just put the 6 on the outside. This does not become the integral from 1 to 3 of f of x dx plus 6. Okay, this is very not allowed. Hold on. Okay, there you go. So this here is very not true. You can't, that is not the constant multiple rule. Constant multiple rule is when it's being multiplied, you can pull out a constant. That's a constant being added, right? So you can't just pull that out. You got to integrate this and then integrate this. So we know that the integral from 1 to 3 of f is 10. And this integral we can find very easily. We did this yesterday. Because what is the graph of 6 going to look like? Just a horizontal line, right, at 6. So if you were to imagine what that looks like, we want the area from 1 to 3. It's going to be just like a little rectangle, right? Where the width will be the change in here, right, which is 2, and the height will be 6, right? So you just have to do the 2 times 6. So this will be 22. So anytime you have a constant in here, it's just the constant times the difference in the limits. This one's a little bit more complicated. We know the integral from -2 to 5 of g, and we know pieces of the integral for f. So let's separate the f and g here into two separate integrals. And then the constant multiple rule tells you you can pull this 3 out in the front. So you can cross off that 3 and pull it out in front. That's what the constant multiple rule says. And which one of these integrals do we already know? The g of x one, right? What is this one? -4. Do we know this one? Kind of. Maybe we can figure it out, right? But they didn't tell us at least explicitly what that was. So we at least know we have 3 times something minus -4, right? Because we know the g of x one. So now we just need to figure out what the integral from -2 to 5 is of f of x. Well, like I said earlier, that's going to be we can break that up, right? We can do -2 to 3 of f of x plus -2 to, or from 3 to 5. Put those two together and you'll have the integral from -2 to 5. That's the property that we were just talking about where you can pick any number. It doesn't even have to be between a and b, but I picked 3 because we know -2 to 3. So -2 to 3 of f is what? 6. What's 3 to 5 of f? -3, right? It's not just 3. You can't just add these together because this one isn't 3 to 5. It's 5 to 3. So if you want to flip it, you got to make it negative. So that'll be plus -3. So this is equal to 3. So -2 to 5 of f is equal to 3. So this is equal to 9 plus 4, which is 13. Any questions about that one? All right, this next part talks a little bit about what we talked about yesterday. Area under the x-axis is going to be negative, right? So if you have two symmetric areas above and below the x-axis, they're going to cancel each other out, right? If you were to add them together, that would be equal to 0. Okay? All right, next page. We're going to talk about some transformations here. So if this is f of x, when you put a negative on the inside, anyone remember what kind of reflection that is when you have the negative on the inside? Y-axis. Negative on the inside is across the y-axis. This is across the y-axis. So as you can see, this function here that was in blue has been flipped across the y-axis. It also happens to be a reflection about the origin, a rotation, because it's an odd function. But it just happens to be the same on that one. This one is an interesting one that we run into every now and then, the absolute value of the inside. What that does is it reflects only the positive side of the y-axis, because it's going to only take in positive x values. It's not going to take in any negative x values, right? So the positive side of this function is over here, right? When x is positive. So this is exactly what the function is going to look like on that side. So then this literally reflects over to that side, and you erase the whole left side. Okay? All right. So let's look at some examples here. I think you're capable of doing A and B on your own here. They tell us the areas in each of these little sections. Well, and then they also tell us that the area from C to 0 is 3, so you can fill in 3 there. I don't know why maybe it was just too small. That's why they didn't write it in. So go ahead and do A and B on your own. go to E, we're doing this right here. 7 is below the x-axis, so it's negative. 10 is above, so it's positive. So this will be negative 7 plus 10, or 3. When we're going from B to D, we're starting at B, going to D. 5 and 7 are both negative. 3 is positive. So this will be negative 5 plus 3 plus negative 7, which will be negative 9. Now we can do some of the weird ones together. Any questions about this? I feel like we're doing pretty good with that stuff. Okay, these two are very different. Putting the absolute value on the inside versus putting it on the outside changes everything. So let's first talk about what this one is. What is this going to do to the function if you take the absolute value of the function? Anything that was negative will become what? Positive, right? Any y value will become positive. So what is this area going to do? Become positive, right? It's going to flip up over the axis, right? So it's just saying take all the area, but it's all positive, right? So we're going from A to 0. But all of that's now positive, right? So you're going to do positive 15, positive 5, positive 3. Or 23. But what's the difference with D, where the absolute value is outside now? Yeah, it's the absolute value of whatever answer you get for that integral, right? It's not making the function positive. It's saying find your answer and then make it positive. So we need to find A to 0 of F. So A to 0 of F will just be as it is, 5, 15, negative 5, and positive 3, right? Which will be 13. And then you make that positive, which that already happens to be positive, so it's not going to change that answer. But if it was a negative 12, then it would become, like, the absolute value of this guy outside would be positive 9, right? But inside, you would then add up all the areas and make them positive. Make sense the difference between where the bars are? Okay, this is the weird one where the absolute value of the x, this is going to reflect only the positive part on the right of the y-axis. So this part here with the 7 and the 10 and the e is going to be reflected, and this is all going to be wiped out, right? It's only taking in positive values of x. So this will be 7, and this will be 10, and this will be negative e. So then we'll add 10, negative 7, and 10, going from negative e to e. We'll get 6. And then this one will be a reflection over the y-axis. So this will still go over to the other side, but then it replaces it on the other side. So this actually reflects everything across the y-axis. This only took half of it and reflected it across the y-axis and erased the other half. And this will be negative e, and this will be negative a. And c will be here, negative c. And so we're only going from negative c to negative a, so that'll be negative 5 plus 15, or 10.
Any questions on those two? This is where a little interesting with their reflections. Okay, lastly, let's talk about what if you are doing a definite integral with a piecewise function, okay? Most of the times you don't have to draw the piecewise functions yourself, okay? You can do, well, eventually you'll be able to do this without a graph. So right now we can use the graph, but we won't have to eventually. So here, if we draw this graph for x less than 3, we'll have a line starting with a y-intercept of 7 and a slope of -2. So it'll go like this. And then for x greater than 3, we're up at 4. A straight line. And we want the integral from 0 to 5. So we're going to have to break this up because we want the area starting at 0 and going all the way to 5. So we'll do the area from 0 to 3 first. But because it's not continuous here, right, and it breaks, we're going to have to start a new integral. So really what we're having to do is break this up into an integral from 0 to 3 of the top function. We'll do that first. That will be this area. And then we'll do the area from 3 to 5. So that will be the area from 3 to 5 will be of the bottom function. And eventually you'll get to the point where you don't need to draw this graph to calculate these indefinite integrals. That's what we're going to learn tomorrow, okay? You're going to find the antiderivative of these, and then you'll be able to plug in those values instead of having to draw the graph. But for now, and so you'll know how to do that without that. But for now, you'll just find the area on there. And if you do that, you should get 12 and 8, which will be 20 total. All right? Have a great rest of your day.